One moment. Good to go. Have a good session.
Thank you. So welcome everyone to the session on lattice cryptography. We will have 5 talks, and each talk will be for 5 minutes. And the questions will be handled after all the talks. So for the speakers, please stay awake until the end of all the talks, and we'll come back to you at the end. So I'm happy to announce our first speaker. Our first talk will be on subtractive sets over cyclotomic rings, limitations of Schnorr-like arguments over lattices, and the talk will be given by Russell A. Russell, please go ahead.
Yeah, thanks for the introduction. So I'm Russell. Can you see my slides? Yeah, okay, so I'm Russell. I'm going to talk about subtractive sets over cyclotomic rings. And this is a joint work with Martin Albrecht. Okay, so let's dive straight into the question. And so the setting of this work is that we consider ring R and let S be a special element of the ring called the slack, and let some set C be an arbitrary subset of R. So given these, we can consider any subset big T of C, where big T is of size small t, and we can define a Vandermonde matrix of dimension T, of T dimension, and where the rows are given by the powers of the elements of big T. And so given this setting, we ask the following question. When are the Vandermonde systems defined by the slack S and the set T solvable over the ring R? And by solving it over R, I mean to find a vector Z of ring element so that it satisfies the given system of equations. So why do we care about this? For the dual Vandermonde system, where it is defined by the transpose of a Vandermonde matrix, we care because we need to solve this kind of equations when we construct the knowledge extractors for Schnorr-like arguments, lattice-based Schnorr-like arguments. And in these arguments, we will use the set C as the challenge set, and the size of the set C is inversely proportional to the knowledge error. And so we want the challenge, so we want this set C to be as large as possible. And the value T determines the type of arguments that we have. So for example, for T equals 2, we have the lattice analog of the classic Schnorr proof. And for T equals 3, we have the lattice analog of bulletproof. So finally, we want that the norm of the slack S and the norm of the elements in C to be short so that our extractor can extract a good witness. So moving to the primal case, we care because we need to solve these kind of systems when constructing lattice-based T out of n threshold primitives by combining almost linearly homomorphic primitives with Shamir secret sharing scheme. And so in these constructions, we will use the set C as the set of evaluation points for the Shamir scheme. And naturally, the size of C is the number of shareholders, n, and T is the recovery threshold. So since lattice-based linearly homomorphic primitives are often only almost homomorphic, but not exactly, so we want, again, the norm of the slack S and the norm of the elements in C to be short so that when we perform linear operations homomorphically, we don't blow up the noise. And so given this, we define the notion of ST subtractive sets. We say that C is ST subtractive if for any T subset big T of C, this divisibility condition is satisfied. And if S equals 1, we say that the set C is subtractive, or we say that there is no slack. Okay, so why do we define subtractive sets this way? It's because if the set C is ST subtractive, then for any T subset big T of C, we have that the Vandermonde systems we've defined by S and big T are solvable over R. Okay, so let me summarize our results of ST subtractive sets over cyclotomic rings. So first of all, we consider the setting of prime power cyclotomic rings, where the ring R is constructed by taking the ring of rational integers, Z, and adjoining it with a primitive p to the 11th root of unity. So in this setting, we have the following positive result. We say we can show that this set C, which is of size P, is subtractive, so there is no slack. And on the negative side, we show that there is simply no subtractive set of size strictly greater than P, and therefore this positive result is optimal in this setting. And next we move to the power of 2 setting, where the ring R is again constructed by taking the ring of rational integers and adjoining it with an mth root of unity. This time m is the power of 2. And so in this setting, we can construct a large family of ST subtractive sets for a wide range of S and T, and they are of different sizes. And as a special case, we show that this set here, which is of size m over 2 plus 1, is a 2-free subtractive set. And in particular, this gives us a lattice-based bulletproof. And on the negative side, we show that there is no family of 2T subtractive sets where the m set of this family is of size strictly greater than m plus 1. Okay, so that concludes the short version of this talk. Thank you.
Thank you, Russell. Please stay here until the end of the session. You maybe ask some questions. So now let's move on to the second speaker. I think it will be Thomas Attema. Thomas, could you please start sharing? Yeah, thank you. So our next talk will be on a compressed sigma protocol theory for lattices, and the talk will be given by Thomas Attema.
Okay, thank you. Can you see my screen?
Yeah, perfect.
So I will be talking about a compressed sigma protocol theory for lattices, and this is joint work with Ronald Kramer and Lisa Cole. So the setting that we are considering is zero-knowledge protocols for general constraint satisfiability. So basically what we aim to do is to devise a protocol for proving that a commitment opening satisfies an arbitrary constraint. So in this case, or in this situation, we capture this constraint by some arbitrary function f, and we want to prove that f of x equals 0, where x is the opening of the commitment. And we want to do this in zero knowledge, so that after running the protocol, no information about this commitment opening is released, except the veracity of this claim. The goal that we are aiming to achieve is that we do this with a low communication complexity for arbitrary functions f. And we want to have a lattice-based instantiation, and we also want to have commit and prove functionality. So basically that the commitment is generated at some point, and at a later stage, a prover is able to prove that this committed value satisfies certain properties. So there's been some related work on this topic on lattice-based zero-knowledge protocols. At Crypto 2018, the first sublinear circuit zero-knowledge protocol from lattice assumptions was introduced. They indeed have a sublinear communication complexity, but their communication complexity is not polylogarithmic. Crypto last year, there was a lattice-based instantiation of the bulletproof protocol. They do have a polylogarithmic communication complexity, but their protocol is restricted to proving knowledge of an SIS preimage. So their protocol does not allow proving that a committed vector satisfies some arbitrary constraint. And also the protocol is not zero knowledge, and it is tailored to a specific lattice instantiation. There are also two concurrent works presented at Crypto this year. So we just saw the presentation by Russell Lai on limits of certain lattice-based zero-knowledge arguments. And I guess tomorrow there will be a presentation in which an application of the theory of sum-check arguments to lattice-based succinct zero-knowledge protocols will be explained. Okay, so another prior work presented Crypto last year is compressed sigma protocol theory. And the high-level paradigm of this theory is that they want to achieve circuit zero-knowledge protocols by solving the linear instances first, and then linearizing non-linearities. And their approach basically starts with a natural sigma protocol for proving linear constraints. So that's much simpler than proving nonlinear constraints. This natural sigma protocol has a linear communication complexity. So they use an adaptation of the bulletproof proof of knowledge to compress the communication complexity of this natural sigma protocol from linear down to logarithmic. So combined, and this results in a protocol for proving linear relations with a logarithmic communication complexity. And then they have a linearization strategy to linearize nonlinear instances. You can apply this linearization strategy in a black box manner, and it uses arithmetic secret sharing. This theory has a number of instantiations. It has been shown to achieve logarithmic communication complexity when it's based on, for example, discrete log or strong RSA assumption. You can even get constant communication complexity under a knowledge of exponent assumption. And you can also instantiate it with pairing-based languages. So a natural question that arises is whether we can also instantiate this theory from lattice assumptions. And that's what this work is about. So we present a lattice-based instantiation of this compressed sigma protocol to you. And intuitively, it's quite clear that you should be able to do this because we have a homomorphic ring SIS-based commitment scheme. And plugging in this homomorphic commitment scheme into the compressed sigma protocol theory should result in circuit zero knowledge protocols with polylogarithmic communication. So this is indeed the case, but some challenges have to be tackled or handled before you get all of this. So we have some standard challenges, such as soundness slack, approximation factors, rejection sampling. These kind of challenges are also encountered in lattice instantiations of standard sigma protocols. So we already sort of know how to deal with them. We do have to be a bit more careful because compressed sigma protocols have a logarithmic number of rounds, where standard sigma protocols only have 3 rounds. So we do have to be a bit more careful. And our contribution in this regard is that we present an abstract framework capturing various design choices. So that simplifies the analysis of these kinds of protocols. So second, we have to be a bit more careful with the extractor analysis. So lattice instantiations typically have much smaller challenge sets and therefore larger knowledge errors. So it's important to have a tight extractor analysis. And prior to this work, there was no tight extractor analysis for these kinds of protocols yet. So that's something that we present. Also, we present a new parallel repetition theorem, and that's required in these lattice instantiations because of this small knowledge error or a large knowledge error. We have a large knowledge error, so we have to repeat the protocol in parallel. And for this reason, we present a novel parallel repetition theorem showing that indeed parallel repetition decreases the knowledge error as we would expect. And finally, we present some adaptations to the linearization strategy that allows us to handle nonlinear instances. So to be able to prove that a committed vector satisfies arbitrary nonlinear constraints. Thanks, that was the presentation.
Thank you, Thomas. A round of virtual applause go to you. So our next speaker is Shu. I hope I pronounced your name correctly. Yeah, we see your slides. Could you please make them full screen? Perfect, thank you. So our next speaker will be Shu Katsumata, who will present his work on a new simple technique to bootstrap various lattice zero knowledge proofs to QRAM-secured NISICs. Go ahead.
Thank you for the introduction. So my name is Shu, and I'm from AIST. So our result in a nutshell is that we provide a simple semi-generic method to construct, wait, can I just change this screen for a moment? How do I erase like my face from the right column side?
We do not see your face. Well, at least I do not see your face. So I mean, I see all your slides perfectly well. I think you can just continue like that. Well,
I think in the upper right, there's a view menu in the native client.
yeah, indeed. You're muted. Sure, you're muted. Oh, you're still muted.
Sorry about that.
Yeah.
Okay, so right, so our result is a simple semi-generic method to construct Coulomb-square lattice-based zero-knowledge proofs. And what I mean by a semi-generic transform here is that it doesn't work for any Sigma protocol, but it does work for a lot of classes of lattice-based Sigma protocols, or in more general, a public coin interactive protocol, so a PCIP protocol. And the thing is, we introduce a new tool called extractable linear homomorphic commitment. And if we plug this in as a wrapper on top of this PCIP, then we'll be able to get a Coulomb-square NIZK. And this will be a proof of knowledge. And it's going to be online extractable, so the proof is easy, and it will be a tight security proof. So again, this work is about NIZKs in the Coulomb. So the prover and the verifier, the honest people, will only query this random oracle in a classical way, but the adversary will be able to make superposition queries to this random oracle. So as any NIZKs in the ROM that we know, so the recipe is that we'll start from a Sigma protocol or a PCIP protocol, and then we'll squash that into an NIZK using random oracles. So this is a brief overview of the known Sigma protocols to NIZK transforms that we know of. Sophia Shamir, I think this is something that everybody knows, and this is what we want to use in practice. So in the classical setting, this is excellent because it works for any type of Sigma protocol. But in the quantum world, things are a bit different because it only works for a type of Sigma protocol known as a collapsing Sigma protocol. And it's unclear whether existing, let's say, when you're giving one Sigma protocol and showing whether it's collapsing or not, sometimes it's trivial, but sometimes it's not. And we don't know whether all schemes are collapsing or not. And so the other transform is the Under transform. So this was really designated for the quantum setting, and it works very well for the classical setting too. But in the quantum setting, what we have is that it works for any type of Sigma protocol. So it doesn't have to be collapsing. But the caveat is that the challenge space that it supports is only polynomially large. So if you have a Sigma protocol that supports an exponential size challenge set naturally, then there's going to be a big proof overhead when you convert it into an NIZK, because you need to do a lot of power repetitions to amplify the soundness error. But the good thing is that the proof of knowledge is straight line. So it has a tighter proof compared to Fiat-Shamir based ones, because the Fiat-Shamir, it requires rewinding. And this is a rough table or a slide about the recent classical ROM lattice-based NIZKs or PCIPs. So as you can see, only the really basic one is secure in the QROM using Fiat-Shamir. And if it becomes a bit more complex, like, so it's not the SIS or the LV relation, if it's a bit more complex and structured, then we don't have to apply the Fiat-Shamir, but we do still know how to apply the Under transform. However, the challenge set is going to be restricted to be polynomially large. So there's going to be a blow up compared to the classical setting where we can use exponential size. And finally, we have these 5-rand protocols, or even larger than 5-rand protocols. Here, it's a bit unclear because we don't know exactly whether the Fiat-Shamir or the Under transform even applies. So this is the current situation. And this is our result, which is a new transform. So it partially answers the question in the sense that it's a semi-generic approach that sits somewhere between Fiat-Shamir and Under. So the property is that, first of all, it works very well with a lot of these lattice-based protocols, or in general, it works for any PCIP with a linear response, which I'll explain a bit later. And as I said, the overhead is somewhere in between Fiat-Shamir and Under. And we have a proof of knowledge, which is can be shown through straight line extractability. So the proof is naturally very simple, and the construction or the idea is really simple too. So most of the arguments are basically classical. So I have like a few 1 minute left. So let me just give you the very rough intuition of the idea. So let's start with a sigma protocol for an SIS-LDB relation. So it's really not important why what these like symbols are. It's just that we have a through-random protocol. And the most important part is that the third flow of the prover is a linear response in the witness E, and this randomness that it used in the first flow R. So for people who don't know about lattices, you could think about Schnorr protocol. It has a linear response too. And when the prover sends this Z as a third flow, the verifier will implicitly check consistency of this witness E and this randomness R in a publicly fashion. And this is how you kind of get a soundness. But when you want to go to proof of knowledge, you need to have two transcripts to extract the witness. And the question is, how do we kind of check this consistency and extract two transcripts without rewinding the adversary? So this is the main idea, which is to just add another consistency check on top of the original protocol. So what we're going to do is that we're going to commit to the witness E and this randomness R through a linear homomorphic commitment scheme. And we are going to add this verifier. There's going to be a new consistency check that checks again about this witness E and this randomness R through this commitment scheme. And it looks really simple. And this is exactly all the construction that you need. And to prove that you can extract is that you kind of have an extractable, if you have an extractable commitment scheme, then you can use statistical arguments to argue that the prover must have committed to some valid E and R in the first round to have non-negligible advantage. So that was a really brief overview, but for more details, you could see the full paper at this link, or I did give an extended 1 hour talk prior to this crypto talk. So please just check it on my homepage. Thank you for listening.
Thank you, Shu. We can move on to the next speaker. Con, could you please start sharing your screen? Thank you. So the next topic is SMILE, set membership from ideal lattices with applications to ring signatures and confidential transactions. The talk will be given by Con Nguyen. Con, the stage is yours.
Okay, thank you very much for the introduction. Hi, everyone. My name is Con. I'm a PhD student at IBM Research Zurich and ETH Zurich. And today I'm going to talk about SMILE, set membership from ideal lattices with applications to ring signatures and confidential transactions. So this is joint work with Vadim Lyubashevsky and Gregor Sila. Okay, so let's start with the set membership proof. Is, as the name suggests, we want to prove knowledge of a secret element small s, which is contained in the public set capital S, without revealing any information about our secret elements. So in this interesting example, we have the set S, which consists of 4 socks, the green, red, blue, and orange one. And let's say I have a green one, and I want to prove that it is in one of these 4 colors without revealing anything about the color. So in terms of applications, it is closely related to so-called one out of many proofs defined by Grove and Kohlweiss, where we want to prove that one of the commitments in the set is a commitment to 0. Then we have the standard transformations to obtain ring signatures, which then can be used to build more advanced cryptographic primitives like confidential transactions or electronic voting and so on. So our main contribution would be we proposed a new lattice-based set membership proof, which is described in more details in the video. And then, the next step would be the standard transformation to obtain efficient logarithmic size ring signature. And then the second part of the paper focuses on, applying this ring signature along with further optimizations to prior work to construct a Monero-like confidential transaction system, which is based on the matrix framework defined by Eskin et al. At CCS 2019. Okay, so the talk is only 5 minutes, so I'll just describe this general approach for proving the set membership. So suppose that this big set S consists of elements S1, S2 up to Sn, so it has size n, and suppose I know Si. So what we want to do is that we can put all the elements of this set S into the columns of the matrix, just like here. So this matrix here has n columns. And then if I can multiply this matrix by this index vector, which has exactly 1, 1 in the ith position and the zeros in all the other positions. And if I multiply this matrix by this index vector, I will get Si. So in this interesting example with socks, I will put all these 4 socks into a matrix, and then I can multiply it by the 0, 1, 0, 0 vector to obtain my green sock. So let this matrix be called P, and then let V be this index vector, which has length n. So I can write this as P times V is equal to Si. And now, well, the naive solution would be to just commit to V, commit to Si, and I will have to prove that PV is equal to Si, which is just a simple linear relation between the committed messages. Obviously, we have to prove that V is well formed. So we have to prove that it has exactly 1, 1, and all the other elements are zeros. But this can also be done using, well, by representing it as some linear or multiplicative relations. So, so for this, we can use some recent lattice-based zero-knowledge proofs, which would give us some, well, concrete and efficient sizes. But the main drawback of this approach is that we have to commit to this whole vector V, which has length n. So, so one can imagine that if the set has like 2 to the 20 elements, then this proof size might be pretty big. So informally speaking, it might suck. So what we need is something sublinear in n. So what we come up with in this set membership proof is a recursive log n round protocol, which, well, so in terms of proof size, it is logarithmic, but it is not really new because some previous works also had the logarithmic proof size. But the core advantage is this concrete efficiency, which will be discussed in the next slide. So I just wanted to point out that that the verification time of our protocol is linear, and this is because the verifier has to process the whole matrix P, which, as I mentioned earlier, has n columns. So this is the main disadvantage. So in terms of concrete efficiency, so for small ring sizes like 8 or 64, we obtain like 16 kilobytes or 18 kilobytes, which is like 3 or 4 times smaller than another ring signature proposed at this year's crypto, the lattice-based dual ring, which has presumably linear size signatures. But the strength of our scheme is that it scales nicely with bigger ring sizes. So for example, for 2 to the 21, it's only 22 kilobytes, which is much smaller than the previous schemes. So yeah, so I'm over 5 minutes, so it concludes my talk. Thanks.
Thank you, Khan. Coming to you. Right, so our next speaker will be Salid Mossel. Salid, could you start sharing your screen? Yeah, perfect, thank you. So the last talk of the session will be on deniable fully homomorphic encryption, and the talk will be given by Salid Mossel.
Hi everyone, so my name is Salid Mossel, and I'm going to talk about the joint work with Shweta Agrawal and Shafi Goldwasser. I will talk about deniable fully homomorphic encryption. Okay, so deniable FHE is the combination of deniable encryption and fully homomorphic encryption. So let's start with some motivation story. Election. So we have 2 candidates, a blue and red, and to vote for the red candidate, everyone votes 0, and for the blue candidate, everyone votes 1. And it's publicly known, so it's in the cloud. Now, the parties, the red and the blue parties, generate their secret key and public key using the key generating algorithm. They keep to themselves the secret key and they publish the public key for everyone to use. Now, Bob used this public key to encrypt his vote, B0, using a fresh randomness R, and then he obtained its encrypted vote, CT0, the ciphertext, and he submitted it to the cloud, so everyone has access to it. Everyone is doing the same and submitting their vote. After the voting phase is done, we can, using the homomorphic property, we can compute this CT star, which obtain the tally of the result. So how many people vote for the blue candidate? Then the parties can decrypt this CT star and know the voting result. Now, for the deniability property of this scheme, so Alice can come to Bob and ask, Bob, for whom did you vote for? And Bob, maybe she's willing to pay him, or maybe he's in love with her and he feels obligated to answer. Anyway, what Bob can do, he can give her his vote B0 and the randomness he used, or alternatively, in a deniable scheme, he can give her the opposite bit and R prime that was obtained using a faking algorithm. Now, Alice, if she encrypts the original message vote and with the fresh randomness, she will obtain the CT star, 0. And if she encrypts the opposite bit using the R prime, she also will get exactly the same ciphertext, CT0. Now, additionally, what we want that Alice will not be able to distinguish whether Bob gave her the opposite bit with a fake randomness using like the fake distribution, or she got something from the honest distribution, where in the fake distribution, the ciphertext is encrypting the opposite bit that Bob gave her. Okay, deniable encryption, it's a notion that was introduced by Canetti, DeWork, Naor, and Ostrovsky in 1997. They also gave a construction from a trapdoor permutation. And in 2014, there was a significant step forward by Sahai and Waters. And our result, we give the notion of deniable FHE. We give a construction based on LWE, which is a polynomial time assumption. Our construction supports large message space. This is the first construction that supports large message space. All the prior construction support 1 bit, and then to encrypt large message, they encrypt bit by bit. We get compact ciphertext, which means that our ciphertext size is independent of the faking probability. And our encryption is in the model of online encryption. We use bootstrapping to obliviously generate FHE ciphertext. And here's some comparison between the prior work and this work. So the only work that gets negligible faking probability is the Sahai Water. We still not achieve it, although we get compact ciphertext, but our encryption running time is depend on the faking probability. So if we want to run polynomial time, we cannot achieve negligible faking probability. Our assumption is polynomial, and also the CDNO is a polynomial, but Sahai Waters is based on IO and one-way function, which is not a polynomial time assumption. And we are the first to support large message space. If you're interested to hear more, you can hear the talk I record, or you can check the paper. Thank you very much.
Thank you, Salit. Thank all the speakers of the session. Now we move on to the question part. I see no questions on the in Zulip. Neither do I see questions on chat. Chris Packett raised his hand. Please go ahead.
Hi. So yes, this is a question for the first talk. If I understand right, you considered prime power cyclotomics and power of 2 cyclotomics only, right?
Right.
Do you have any sense about what can be said in more general composite cyclotomics, or even other classes of rings, maybe multi-quadratics or something of that nature? Did you look into that at all?
To be honest, we tried a little bit for like the mth cyclotomic ring, where m is composite, but we didn't get very far. So it was, and I think, so if I remember correctly, nothing very interesting is going on. So you can just split it with CRT and then things follow. So you don't get anything surprising there. But I forgot the details.
Mhm.
And for other kinds of rings, so other than cyclotomic rings, we have no idea.
Great. And the set, just to follow up, the set that you identified in prime power cyclotomics, those are the so-called cyclotomic units, is that right?
Yeah. I think like they are like some of the cyclotomic units, but not all, if I remember correctly. Yeah.
Right. Yeah. Well, that's an infinite group, so yeah. But the usual generators, I guess, of that.
Yeah.
Yeah. Thank you.
All right, so we have two more questions. So the one question is in the Zulip chat, and the question goes to Shu. The question by Watson Led, and it asks he asks the following: does your technique also sharpen the security reduction for the ZKP scheme?
Security reduction as in security loss? In that case, yes, it does. Depending on, I guess, where you compare it with, but if you're comparing with Fiat-Shamir, then it does provide a more tighter security reduction. And compared to Unruh, I haven't checked, but maybe it's about the same, or our scheme might be slightly worse or somewhere with these like query bounds. I'm not quite sure about that. I hope that answers his or her question.
I hope so too. If it doesn't, please continue the discussion in Zulip. Okay, our next question was asked on chat, and the question goes to Khan. The question is the following: is the ring signature you mentioned in the random oracle model?
Yeah, so we transform our set membership proof into the one out of many proof, and then the ring signature is just the proof using the Fiat-Shamir transform. So yeah.
Yeah, thank you. Right, so the next question is from James Hughes. He asks Salid, so he asks the following: if the voting software creates two votes with R and R prime, providing the voter with both R and R prime, so the system works, what stops the software from sending in the wrong vote?
I hope I understand the question correctly. So the ciphertext will only decrypt to one vote, to the original vote, like the alternative, the faking bit. It's something we hide inside the encryption. So it will give the exactly same ciphertext, but the decryption will always be the correct one. And the secret key is what stops the software from sending the wrong vote.
All right, thank you, Salid. I see no further question from the audience. I have a couple questions too. So my first question is for Russell. It's regarding the subtractive set definition. Am I understanding correctly is that you give a sufficient condition, but is it also a necessary condition? Maybe you said it already, but I think
yes,
you give a condition.
It's a sufficient condition. We didn't investigate if it's necessary. I don't think so.
I see. Okay, you don't think so. Okay, that was my next question. So you believe it will be a bigger set, right, that can be used?
I mean, so my gut feeling is that sometimes you are lucky and things cancel out. So yeah.
All right, thank you. Okay, we have one more question to Tomas. So the question is, why do you need the special result of parallel composability?
So to the best of our knowledge, there were only parallel composition results studying soundness and not knowledge soundness. So showing that parallel composition reduces the soundness error. And we actually needed a result that shows that parallel composition also reduces the knowledge error of protocols. So this is slightly stronger, but we heavily rely on prior results to achieve this.
All right, thank you. So I also have a question to you. It's not regarding your 5-minute talk, but on your longer talk, you mentioned that you need a ring, you rely on the rings assumption. Do you really need the ring structure, or is just for convenience that will probably simplify or make your construction more efficient?
Do we need the ring structure? So basically, we need a module structure. So we need to be able to so we have a group element and a ring, and we need to be able to multiply this group by ring elements. So yes, I think we really need this.
I see. Thank you very much. Thanks. Mm-hmm. Well, if you have more, if anyone has more questions, please ask now. Well, otherwise, I have one more question to Smile, to Con. So you're targeted to make your scheme more efficient with respect to the ring size, right? But what about the computation complexity? Or maybe I misunderstood your table when you wrote when you gave the kilobytes and megabytes with respect to the ring sizes. Was this the computation time, or was this the size of the keys?
Yeah, it's a signature size. So in terms of computation, it's not very good. So the prover time is linear, but I guess the worst thing is that the verifier's time is linear, because there is this huge matrix, and then the verifier has to like compute operations on that matrix. So it's not.
I see. So, and also maybe my last question to you is, well, is there a relation between your work and what's called the private set intersection? Because it looks like what you're doing is a special case of this. I mean, the set membership is a special case of the private set intersection. Are you aware of any construction that is similar to yours?
Yeah, I don't think I'm not. Yeah, I think I'm not aware of anything similar for PSI.
Okay. All right. So I see no further questions, and I also exhausted my questions. In that case, I think we're good. So thank the speakers once again.